This video is brought to you by IXL, used by millions of students worldwide to get ahead in math, English, and more.
This video is about volume and surface area of similar solids. Similar solids are three-dimensional figures that are the same shape but can be different sizes. They also have proportional sides, which means all of the ratios of corresponding lengths are equal to the same scale factor. Here, you can see two similar rectangular prisms. Note that they're the same shape but different sizes. Here's an example of two similar triangular prisms. Now, let's talk about the relationships between similar solids. This is a cube with 1 centimeter side lengths. This is a similar cube with 2 centimeter side lengths. The scale factor between them is 2, which means the ratio of lengths in the larger cube to the smaller cube is 2 to 1, or 2. Next, let's find the ratio of surface areas. In the smaller cube, each face has an area of 1 square centimeter, so the total surface area of all 6 faces is 6 square centimeters. In the larger cube, each face is a 2 by 2 square, so the area of one face is 4 square centimeters. Since there are 6 faces, the total surface area is 24 square centimeters. The ratio of the surface areas is 24 divided by 6, or 4. Lastly, let's find the volumes. The smaller cube has a volume of 1 cubic centimeter, and the larger cube has a volume of 2 times 2 times 2, or 8 cubic centimeters. The ratio between these volumes is 8 to 1, or 8. Do you notice a pattern in these ratios? They're all powers of 2. 2 is 2 to the first power, 4 is 2 to the second power, and 8 is 2 to the third power. Since 2 is the scale factor between these similar figures, the ratio of lengths is 2, the ratio of surface areas is 2 squared, and the ratio of volumes is 2 cubed. This pattern applies to all similar solids. The ratio between lengths is equal to the scale factor. The ratio between surface areas is equal to the scale factor squared, because surface area is a two-dimensional measurement. And the ratio between volumes is equal to the scale factor cubed, because volume is a three-dimensional measurement. We can write these relationships using equations. If we label our lengths L1 and L2, then the scale factor is the ratio L1 divided by L2. If we label the surface areas S1 and S2, the ratio S1 over S2 is equal to the scale factor squared, or L1 over L2 squared. And the ratio of our volumes, V1 over V2, is equal to the scale factor cubed, or L1 over L2 cubed. In summary, the ratio between the surface areas is equal to the square of the ratio between the lengths. Similarly, the ratio between the volumes is equal to the cube of the ratio between the lengths. Let's put this information into practice. In our first example, we're given two similar solids, and we want to find the surface area of the larger rectangular prism. Let's call the prism on the left figure 1 and the prism on the right figure 2. By the way, it doesn't matter which ones we call figure 1 and figure 2, as long as we're consistent. In this problem, figure 1 has a side length of 12 centimeters, and we need to find its surface area. Figure 2 has a side length of 4 centimeters and a surface area of 8 square centimeters. Remember, the ratio between the surface areas of two similar figures is equal to the square of the ratio between the lengths. If we substitute 12 for length 1, 4 for length 2, and 8 for surface area 2, we can solve the equation for surface area 1, or S1. On the right side, 12 divided by 4 is 3, and 3 squared is 9, so S1 over 8 equals 9. Now we can multiply both sides of the equation by 8 to find that the surface area of figure 1 is 72 square centimeters. Here's example 2. The solids below are similar. What is the volume of the smaller cylinder? First, let's label the cylinder on the left as figure 1 and the cylinder on the right as figure 2. We know that the ratio between the volumes is equal to the cube of the ratio between two corresponding lengths. Since we know the length of the radius of both cylinders, we can use 5 inches for our length in figure 1 and 3 inches for the length in figure 2. So if we substitute 500 for volume 1, 5 for length 1, and 3 for length 2, we can solve the equation for volume 2, or V2. First, we can cube the lengths to find that 500 over volume 2 equals 125 over 27. Now, to get rid of the denominators of our fractions in this equation, we can multiply both sides of the equation by 27 and V2. Canceling common factors on both sides gives us 13,500 equals 125 times volume 2. Finally, we can divide both sides by 125 to find that volume 2 is equal to 108 cubic inches. In example 3, we once again have two similar solids, and we want to find the ratio of the larger cube's volume to the smaller cube's volume. Here, we can label the larger cube as figure 1 and the smaller cube as figure 2. The ratio between the volumes is equal to the cube of the ratio between the lengths. The side length of figure 1 is 20 centimeters, and the side length of figure 2 is 10 centimeters, so we can substitute 20 and 10 for length 1 and length 2. Notice that we aren't given any volumes to substitute for V1 or V2. So our equation is V1 over V2 equals the ratio 20 over 10 cubed. Since this question is asking for the ratio of the cube's volumes, we're going to solve this equation for the ratio of V1 over V2 by simplifying the right side. 20 divided by 10 is 2, and 2 cubed is 8. This means that volume 1 over volume 2 equals 8, so the ratio between the cube's volumes is 8 to 1, which we can write as a fraction, 8 over 1, or with a colon, 8 to 1. In this last example, we have two similar solids, and we want to find the ratio of the smaller cone's height to the larger cone's height. Let's label the cone on the left as figure 1 and the cone on the right as figure 2. The ratio of surface areas between figure 1 and figure 2 is equal to the square of the ratio of any two corresponding lengths on the cones. Figure 1 has a surface area of 49 square millimeters, and figure 2 has a surface area of 121 square millimeters. If we substitute these values for surface area 1 and surface area 2, we can solve for the ratio L1 over L2. Since that ratio is squared in our equation, we can take the square root of both sides of this equation. To take the square root of a fraction, we just take the square root of the numerator and the square root of the denominator. The square root of 49 is 7, and the square root of 121 is 11. On the right, the square and the square root cancel, so we see that 7 over 11 is equal to length 1 over length 2. If we think of length 1 as the height of the smaller cone and length 2 as the height of the larger cone, this means the ratio between the cone's heights is 7 to 11. Thanks for watching. I hope this video has given you the confidence to master this skill.
Head over to IXL.com for more practice on this skill and thousands more videos in math and language arts.